Okay, page 11 of vectors. They introduce here three-dimensional coordinates with vectors. Okay, I'm not sure if you've done three-dimensional coordinates before, but when they're drawn out here, you can see that the yellow dimension is in the x direction, the green dimension is in the y direction, and the red direction is the z direction, and those are the positive directions shown there. Okay, let's see. So the I component vector would look like 1, 0, 0 because it's in the x direction, and j would look like 0, 1, 0, and k would look like 0, 0, 1. Okay? The magnitude of a vector. So the way you find the magnitude of a three-dimensional vector is similar to the way you do it for a two-dimensional vector. It's kind of like with Pythagorean's theorem, but it's like a three-dimensional Pythagorean's theorem. It looks like this. Okay? Let's see. If point A is x1, y1, z1, and point B is x2, y2, z2, and if there are 2 points in space, then you can find the vector AB, subtracting the position vector OB minus the position vector OA. So you would take x2 minus x1, y2 minus y1, and z2 minus z1. Okay, and the magnitude of vector AB is equal to square root of plus y2 minus y1 squared plus z2 minus z1 squared. Okay, vector equality. Two vectors are equal if they have the same direction and magnitude. Okay. If A is A1, A2, A3, and B is B1, B2, B3, and A is equal to B, then that's the same thing as A1 is equal to B1, A2 is equal to B2, and A3 is equal to B3. If A and B do not coincide, then they are the opposite sides. And they're talking, and I should have put bold here, vector A and B. So we're continuing to talk about these two vectors A and B, which are equal to each other. Okay, so they are equal to each other. So if they're not exactly on top of each other, which is what I mean by when they say if A and B do not coincide, they're not on top of each other, then they look like this. They're on opposite sides of the parallelogram and they lie in the same plane.